Hello students, welcome to the course on Hydrology EVE 301 offered to civil engineering students at College of Science and Technology. I am Kirtan Adhikari, faculty at CST. See you in the course.
Let's continue our discussion with measurement of evapotranspiration. Measurement of evapotranspiration for a given vegetation type can be carried out in two ways: using lacymeter or field plots, and there are many methods to estimate the evapotranspiration, such as Penman equation and Ballic formula. Lacymeter is a watertight tank containing soil which is set in the same surrounding as that of the field, and it is buried to the level of natural soil. As you can see in these images, these are the lacymeter constructed over a field. Plants are grown in it as in the neighborhood as shown in the image. So here, when the plant is grown, the plant is also grown over the lacymeter, as same plants are also grown in the vicinity. Okay, the evapotranspiration is estimated in terms of amount of water required to maintain constant moisture condition within the tank, measured either volumetrically or gravimetrically through an arrangement made in lacymeter. So in this case, I have simplified this lacymeter just to give you an insight of what the lacymeter looks, but here many arrangements are sometimes made to do the readings. And like I said, there are many equations available, so let's discuss these equations. To begin with, let's discuss the Penman's method. To compute the evapotranspiration from a plot, we can use this expression whereby evapotranspiration, the potential evapotranspiration or the consumptive use, is equal to A Hn plus Ea gamma divided by A plus gamma, where A is the slope of the saturation vapor pressure versus temperature curve at the mean temperature in degree centigrade per degree centigrade. Okay, and Hn is the net radiation in mm of evaporable water per day, whereas Ea is the parameter including wind velocity and the saturation deficit. Okay, and gamma is a psychrometric constant. And further, Ea is given by this expression, which is 0.35 times 1 plus U2 divided by 160 times the saturation deficit. Now here, one thing to understand is, in our previous equations like Mayer's formula and Rohr's formula, which we used to compute the evaporation from the lake or the water bodies, we use velocity at certain height in kilometer per hour. Here the velocity is considered at the height of 2 meters from the ground surface, and the unit has to be in kilometer per day. We have to substitute this unit in kilometer per day, then only our equation will give us the correct answer. And Hn is the Hn is the net radiation in mm of evaporable water per day, and further this Hn is given by this expression, whereas Ha is the incident solar radiation outside the atmosphere on a horizontal surface. R is the albedo, phi is the latitude. This n by n is a ratio of actual sunshine divided by maximum sunshine over this latitude. Okay, and the sigma is the Boltzmann constant. Temperature is in Kelvin, which is raised to power 4. We have to notice this, that the temperature here we have to substitute in terms of Kelvin. Okay, and Ea is the actual vapor pressure of the air. And you also might have noticed that I have highlighted certain parameter with blue color. These are the parameters which we have to retrieve the value based on latitude from the standard table. So we will get the value from table based on the latitude. Ha we are going to get it from the table, and the n, okay, the maximum amount of sunshine hours in particular latitude, we are going to get it from a table. Standard table is available, so these three values we will have to retrieve from the table, whereas R is a constant, also known as albedo, so it is a reflective property, right? So here are some constants given for different type or soil type, or not the soil type, different soil cover, okay, land cover. And here, as I said, temperature has to be in Kelvin. So with this, let's solve a numerical. The question states, calculate potential evapotranspiration from a watershed located in southern Himalayas of Bhutan for the month of June using Penman's approach. The following data are available. So the latitude is given to us, it is 27 degrees. Elevation is also given, which I don't think we'll have to use this. A mean monthly temperature is given as 32.5 degrees centigrade, but please note that we have to use this in degree Kelvin. Relative humidity is given 87 degrees, 87%, okay. Mean sunshine or mean observed sunshine hour is 7 hours, and wind velocity at a height of 2 meters is given kilometer per hour, so many kilometer per hour, so we have to convert this into kilometer per day. And the nature of surface is also given, it is close ground green vegetation. So I believe that the value for albedo for this condition is 0.25. so like I said, there are A, Hn and N value have to be retrieved. This value has to be retrieved from table. So I have already retrieved the value for A, which is 2.07 from table number 3.3 from Engineering Hydrology by Subramania, okay. And HA, the value of the HA based on the latitude I have just snipped out for the month of June, and similarly for the value for N I have just snipped out from the table, okay, standard table for the month of June. Now here thing is, we are interested to find the value of HA and N at the latitude of 27 degrees, but in our standard table, the standard table does not have 27 degrees. It simply have 30 degrees, which is 16.5, and 20 degrees, which is 15.8. For 27 degrees we have to interpolate. Interpolate means we have to estimate the value at 27 degrees. For this we use a special technique known as a linear interpolation. If you consider this as x value and this as y value, again this is x1 and this as y1, then you will get 2 points. If you join a line, then you will get a straight line between 2 points, right? That's why we call it linear. So we are assuming that the points that is joining these two dots are lies on a straight line. So our interest is to find the x-y coordinate of this point. In fact, we already know the x coordinate, which is 27 degrees, but we are interested to find the y coordinate. For this, if you observe, there are two triangle formation here, right? There is one a big triangle and there is a small triangle, and these two triangles are similar triangles. So from the property of a similar triangle, which states the ratio of their base to height, ratio of their height to base should be same. So x divided by 27 minus 20, right, this distance 27 minus 20 should be equal to this height, which is 16.5 minus 15.8 divided by this length, which is 30 minus 20. So I have put this in terms of equation here, and from this I have expressed everything in terms of x. If you notice, 16.5 minus 15.8 divided by 30 minus 20 is change in y divided by change in x, which is nothing but the slope of this line. So from here we can get the value of x is equal to base of a smaller triangle times the slope of this line. But our interest is not to find the x, our interest is to find the y coordinate. So y coordinate is going to be 15.8, this value, this line, right, plus x. So here if I substitute the value of x in this expression, I'm going to get the value of HA at the latitude 27 degrees. So what I did is I have expressed this, the whole thing, I have substituted the value of x in here, and instead of writing 27 I have just replaced it with L, indicating latitude. So I get an expression for HA which is valid between 20 to 30 degrees, which is 15.8 plus L. L could be between 20 to 30 minus 20 times 0.07. 0.07 is the slope of this line, which is y is equal to C plus mx, C plus mx, or mx plus C, right? So I have derived this equation. Similarly, you can also derive such equation, but be sure that the application domain, now if the value was 20, anywhere between, if the latitude was anywhere between 20 to 30, this equation is valid. But if it is 35, then again we have to derive a different equation for that. Okay, so this is a simple technique which is extensively used in engineering. Okay, be it for your design purpose, for any or any other subject, we use linear interpolation if we have to retrieve some value from the table. So please understand this method well. Okay, likewise, I have also done the linear interpolation for the value of n. So I have already got the value of HA and n. With this, let's solve this problem. So first I start by calculating the variables that is required to be substituted in the Penman's equation. I need the saturation vapor pressure. Notice that I have modified this equation. Okay, so now I will directly get the value in mmHg. So when I substitute the value of temperature in degrees centigrade, please be careful where you have to put in degree centigrade and where you have to put in degree Kelvin. So here I put in degree centigrade. Likewise, I can calculate the value of actual vapor pressure, which is nothing but the saturated vapor pressure times the relative humidity, and I get the value 31.933 mmHg. Likewise, I'm converting the velocity from kilometer per hour to kilometer per day. It's almost equal to 85. With this, let's calculate the EA. It's a parameter that also considers the velocity and the vapor pressure deficit. So after substituting the value, we are going to get 2.577 mm per day. Likewise, we can calculate the value of Hn. I said to calculate the value of Hn, Ha has to be retrieved from the table, N has to be retrieved from the table, which I have already did. So this is a constant. Here the temperature has to be in degree Kelvin. Rest, this is actual vapor pressure. We simply substitute it here, and this we are going to calculate. So n equal to 7 hours was given in the question. Capital N we calculated from the table, we interpolated from the table. Yes, now n by n we are going to get 0.505. Likewise, I am doing a simple calculation of sigma t raised to power 4 outside, so that this equation does not become too long. So here I'm going to get 17.508. so with this I can substitute this known value in my Hn equation, and then I get value of 5.976. Further, I can put the values of all these parameters of the Penman equation, and then I get the potential evapotranspiration as 5.325 mm per day. Please check this calculation once yourself and be careful. Let's continue our discussion on computation of evapotranspiration. The second method we have here is Ballic gradual method, and it is an empirical method, and it is used extensively by field engineers and irrigation engineers and agriculturists to estimate the potential evapotranspiration, also known as consumptive use, of various crops by correlating sunshine with temperature. The main governing equation is the potential evapotranspiration is equal to summation of K, which is the monthly crop coefficient. This coefficient would be different for different crop, and F, which is the monthly consumptive use, which is further given by this expression, whereby Tm is the monthly mean temperature in degrees centigrade, and P is the monthly percentage of hours of bright sunshine in the air. So this method is relatively easy compared to the Penman method, because it is empirical equation first of all, and it has very less parameter compared to the Penman equation. With this, let's solve a numerical. Question states, use Ballic gradual method to calculate consumptive use, that is PET, for rice crop grown from June to August in Paro at latitude of 27.42 degrees north from the following data. Find the net irrigation demand for rice using the given rainfall during the period. So here what we need to understand is the consumptive use means that much of water is required, but if there is a rainfall, then we have to subtract the rainfall from this value to be supplied. The consumptive use means that much of water, in another sense, that much of water has to be supplied to the field. But if there is a rainfall, so some part of the consumptive use is compensated by the rainfall, so we'll simply have to subtract this. Okay, having that much of idea, let's go and solve this. So for this, the value of K will be given. It's a constant. Okay, it is computed based on experimentation for different crop. P will have a different table, just like in Penman's method. P is the value that we have to retrieve from our standard table. So with this, what I have done is, I have, just like in previous example, I have already interpolated the value for June, July and August. Okay, and this value is coming from the table. As you can notice, the value for 30 is available, value for 25 is available, and 27.42 is not available. For this, we have to use the interpolation, linear interpolation technique, which we have discussed in previous lecture. So based on this, I have computed the value for the monthly percentage of sunshine hour for June, July and August, and for rice crop I'm using the coefficient K as 1.1. I've simply taken the value from here. Okay, with this, let's go further and do the calculations. And monthly consumptive use is given by this expression. We simply have to substitute the value of temperature and value P we have just retrieved, we have just calculated. So accordingly, we can calculate for June, July and August, and the PET, that is potential evapotranspiration, is the summation of K times the monthly consumptive use, which is 1.1 times this value, 1.1 times this, 1.1 times this, we will get this value. Further, we have not entirely solved the problem. If the question was just asking us to find PET, then we have done it, but the question is also asking us to find the net irrigation demand. For that, we have to subtract the rainfall. Now, as you know, all the rain that is falling over a field, some portion of rain will go as an evaporation, right, which is not available to the crop. So for that reason, we have to use the effective rainfall. Effective rainfall means after deducing such losses. So here, just an assumption, we are making an assumption that 20% of the total rainfall is getting lost. Okay, so only considering 80% of the actual rainfall, which is whatever rainfall was there, we are just considering 80% of that, and it for every month, so we get this value. So after that, the irrigation demand would be, like I said, PET minus the effective rainfall. Let's say there was no rainfall, so our net irrigation demand would be simply PET, which we have already calculated. Finally, we substitute this value. Notice that I have modified here as this value minus the effective rainfall. Okay, this is true for this particular question. If there is no rainfall information provided, then you can simply ignore this, and finally when you add this up, you'll get 45.95 centimeters. So that much of water needs to be supplied to the rice crop if you are growing in Paro in the month of June, July or August. With this, I have a homework question for you. Okay, I have provided the data set. You are expected to use both the method, Penman's method and Brindley-Carter method, to find the PET for all the months. And the next part of the question says to make a computer program. So I have made a computer program, so I will quickly demonstrate you how to do this. Okay, we are now on console. So I have already created a Python file. I have developed the program. So in this program, we are going to solve the numerical from our reference textbook, that is Engineering Hydrology by Subramania. So here, the month that you are interested, the question says I'm solving 3.3. okay, this is Engineering Hydrology by K. Subramania, 4th edition, example number 3.3. So here the month is November, so I'm putting 11, and temperature is given 19 degrees centigrade. Okay, latitude is given as 28 degrees 4 minutes, so which is equal to 28.0666. okay, I have to supply this in decimal degrees. So that was the latitude. Next is relative humidity. Relative humidity is given as 0.75 in the question, and wind velocity is given as 85 kilometer per day. Next is albedo is taken as 0.25. So here, and again, sunshine hour. The sunshine hour here given is 9 hours. So the program ran and it is giving us the solution which exactly matches with the solution answer given by the textbook. Okay, now we can also quickly check the values that we have got in this example. Okay, I have done the manual calculation and now we can check using the program. So let's quickly note down the parameters that is given in the question. The latitude is 27 degrees, temperature is 32.5, relative humidity is 87%, N is 7, velocity is 85, R is equal to 0.25, and the PET we got it from this question from manual calculation was 5.325. So let's quickly go over the console and try to solve this using the program. Okay, now we are on console. So let me clear this first. Okay, I'm running a program now. The month we are interested is June, that is 6. Temperature was 32.5. Latitude is 27 degrees. Relative humidity is 0.87. Likewise, velocity is we have 85 kilometer per day, and albedo taken was 0.25, and further the sunshine hour was 7 hours. So here we got the solution, and like in our manual calculation, the answer exactly matches, which is 5.32 mm per day. So our program is absolutely working. So I also expect similar program from you people taking hydrology as a major course. I believe it is necessary for all of us to be able to use such tools and technology to solve the problem. It will be really beneficial for you people when you take research in your final years. Okay, with this I conclude this lecture. Thank you.